Hello and welcome to Engineering Economy. This is Dr. Ala Kamerdiner. Today we will talk about other analysis techniques. Specifically, we will talk about future worse analysis, benefit-cost ratio or present worse index analysis, payback period, and last but not least, we will talk about sensitivity, break-even, and what-if analysis. So our learning objectives for today is to be able to apply future worse analysis and benefit-cost ratio analysis. We will also be able to understand the meaning of payback period. And we will be able to conduct sensitivity, break-even, or what-if analysis for solving engineering economy problems. Let's take a look at the clean green office buildings. So what could be the advantages of green office buildings? Well, first of all, they could improve workers' productivity, and they might be able to reduce health and safety costs. They can also improve indoor environmental quality and reduce energy and maintenance cost. An example, is the buildings that have better energy cost would be some buildings that are equipped with, for example, solar panels. So, of course, there are some really great advantages of green office buildings, but what are disadvantages, if any? Yes, there are some disadvantages. Specifically, these buildings tend to cost more to build, so there's higher initial costs, and therefore it makes harder to recoup the investment in a timely manner. So when you think about these topics that we will discuss today, I want you to think about this ideas of green office buildings and try to answer these questions as we go in and learn these new topics. So question is, what is what is the difference between these non-traditional green office buildings? For example, office lease usually requires building owners and not tenants to pay for heating and cooling costs. So how might it affect potential green building tenants' decision? Another question, and it's kind of like another side of the same coin, is that green building developers sometimes prefer renting the building out rather than selling them. So a quick question is, what do you think are the factors that might influence their views, the developers' views? And also, how might architectural features or better materials or better workmanship make green building more attractive? There's some other questions that I want you to think about. How can the cost and benefits of green building be economically validated? Does the economic attractiveness of green building depend on which measure is used for evaluation? What ethical questions arise from state or municipal regulations that are intended to promote or require green building practice? Alright, so let's talk first about future worse analysis. So that's a method for comparing alternatives that allows us to compare different projects or different alternatives in terms of future worse at a given point of time in the future. So here's an example. How much could one accumulate by age 65 if $35 is saved each week from age 20? So you can see here in this example, we're asking about how much we will have in the future at the age of 65. We're thinking about age of 65 being future and age 20 being the present. And so the savings, some of the information that's also included is that saving account pays 5% interest compounded semi-annually. So when I look at this wording, I see right away that it says compounded semi-annually. That tells me that the compounding period is half a year, and when I see 5% interest, I know that it must be a annual nominal interest rate, even though these words like annual and nominal are not included, but I still understand from the way it's written that it must be, this 5% must be a nominal and not an effective rate. So we'll take that into account. And so because we have semi-annual compounding periods, even though it says years from 20 to 65, and so if the age 20 is 0, then the age 65 would be 65 minus 20 would be a 45-year period. Because we have half a year as a compounding period, it's going to actually be not 45. Our number of periods, compounding periods, would not be 45. It would be twice as many, because the year is not a compounding period, but half year is. So we would have 45 times 2, 90 compounding periods. So again, how do we find the effective interest rate? Well, we'll look at the nominal interest rate of 5%. We're going to find an effective semi-annual rate by dividing by the number of compounding periods per year, which is 2. So 5% divided by 2 would be 2.5. And so again, right, we're saving each time, we're saving 35, but that's saved each week. This amount does not grow every week, because the week is not a compounding period. Half year is compounding period. So what we do is we accumulate all the weeks in half a year, and that would be basically depositing all these weeks throughout half a year would be the same as if we deposited all that amount at the end of half year. So what it means is that the 35 per week we multiply by the number of weeks in half a year. And in a year we have 52 weeks. Therefore, in half a year we have 52 divided by 2, which is 26 weeks. Therefore, semi-annual savings are $35 multiplied by 26 weeks. $35 per week multiplied by 26 weeks. And that relates to 910. So this is every half year, every compounding period, we have this equal payment. So we can use a uniform series uniform series formulas. And so this is A for purposes of analysis. This is A. So we want to find F, right? Because we want to find value in the future. Age 65 is in the future with respect to age 20. So future worth equals to this A, the value of A, right? So FA, so therefore the discount factor is also FA, right? FA here and also FA here. So then this is the I and this is the N. And again, I just explained how we got the I. I is basically found by using this formula, right? That's an effective semi-annual rate. And it's using the formula R over M, where R is a nominal rate per year and M is the number of compounding period. And R is 5% and M is 2, so 5 divided by 2 is 2.5. And then this 90, this is our N. And again, I already have explained that if we have 65 as a future year and 20 as 0, then we have 65 minus 20, 45 years. But because the compounding period is half a year, then we have 45 multiplied by 2, 90. And so now we have, after evaluating the F given A with these values of I and N, we get this much, and so we multiply these two to get the value. So in case we don't have 2.5, so again, usually we go in the textbook and look up the tables, or alternatively we could check the formulas and plug in the values of I and N directly in the formula for F given A. But I wanted to also show you an alternative approach, just how we can do that, how we can compute this using simply an Excel. So I open the Excel sheet, and so I could use and introduce 910. But if I just wanted to compute this F given A factor, if I wanted to find F given A factor for 2.5% and 90, right? If this is what I wanted to find, I can do it simply like this. I can use a future value, right? Because we're looking for future value. So fv is this function, right? And you can look it up if you wanted to. So fv function is the function that gives us the future pay value. And so I can actually find and it tells me, right, the rate. So I can use the rate here, 2.5%. And then number of periods is 90 periods that we have. And then here's the payment. The only difference about the payment is, remember, I discussed this earlier when we talked about the future values, and it should be minus 1, right? So instead of 1, it should be a negative. So if I put -1, that gives me exactly, notice that gives me exactly this value here of the discount factor. Alternatively, right, and then I could just multiply these together to get the value if I wanted to, right? So if I have this my 910, and then I can multiply these together to get the value. Well, let me use. All right. So to get this value right here, right? So 299,578, and that's what we get approximately 572. That's what we get approximately. Or I could use a future value there too, and I could right away find this value just using the future value. So let me make it a little smaller. So I can find the future value again using fv function, and then my rate is 2.5%, and number of periods is 90, and then I use minus 910 as the payment. And so again, right, there is a little bit of right, because this is actually 392.15 and this is 392.2. If we used instead 329.2 and then multiplied this times this, we would get this value. So you can see, right, this is just not this is more precise, but again, right, this is an alternative way to do it. So there's a little bit of discrepancy, but because these are large numbers, for example, number of compounding periods is rather large, so then, you know, if we approximate, it's not really 329.2, but either way, right, if you do it, it will give you a pretty close values. So I just wanted to demonstrate to you how we can use this FV formula to compute the future wars. Alright, so continuing on, let's talk about additional things regarding future wars analysis. So we have a new plant and remodel. So new plant requires, in the first year, it's gonna give us 85,000 versus for remodel we have 850, and then again the 200,000, and so that gives, you can see that this is what we get from new plant, and this is what we have, the benefits that we have in terms of remodel. So because the new plant, there's additional costs, so we'll get these costs represented by a cash flow diagram. So you can see here, right, the 85,000 in year 0, 200,000 in year 1, and we have 1,200,000 in year 2, and then 200,000 in year 3. So that this cash flow diagram represents a new plant. And so we want to find what's the future worth or future worth of new plant and compare it with the remodel. So therefore what we're gonna do is this 200,000 that's in year 3, it's already in the future. But the rest of them, they need to be discounted. For example, right, the 85,000 is the present with respect to the future. So we can just say 85,000 is the present. We want to find the future, FP. And so here we have FP as discount factor. The 8% is the interest rate in this example. And then 3 is the number of years, right, between the present and the future amount. Then the 2,000, we could look at this as 200,000 here, and then again 200,000 here, and then again 200,000 here. So again, it depends on how you look at it, right? If you wanted to just look at these as A, rather than have it separately. But there's another way to do it where we just have this already without discounting and only discount this one also as a present, and then we have just, instead of 3 we could have 2, and here just 1. Or we can look at this as all these 3 2,000, a little piece here of 2,000K, and this 200,000K. Look at them all together and look at them at the uniform series. And so here in this solution we look at them as a uniform series. So then we have this uniform series of 200,000 in year 1, 2, and 3. And then in year 2 there's an additional million on top of it, so that's a million here. So again, right, if this is A, then we're looking for a future value of all 3 of these pieces. And so F given A, 8%, 3, and then this is of course is a present with respect to the 3, but there's only 1 year in between, therefore n is as 1. And so after we plug in the values of the discount factors and multiply and sum, then we get this value, which gives us the future value of the new plant. And of course we need to compare it to a remodel. So this is the cash flow diagram for the cost of remodel. And so these are the costs, right? You can see the arrows pointing down. So these are the costs and these are the costs. So then keep in mind that we can compare the future worth of cost or future cost. So then we look at the future worth of remodel. Again, we have 250K, 250K, and again 250K. We can look at all of these as a uniform series during the 3 years, and this is the present. So very similar to how we computed the new plant, we can find the future value of remodel, where 850,000 is the present. So FP here, there's 3 compounding periods between the present and the future, so 3 here, and then these 250 during year 1, 2, and 3 are annual. So this is A, and then we have F, so FA as a discount factor, right? It's just the same because here we have F and this is the A. Then again, in the same order we have F, A in discount factor, and then 8%, 3, because this is for 3 discounting 3 compounding periods. So then when we plug in the values of discount factors, and we can find them easily, right? We can either use formulas or we can find them easily on the page for 8% tables in the textbook. And then looking at the columns for FP here and FA here, and the row is going to be 3. So that gives us this much, right? So after we evaluate this expression, we'll get this much. So now the question is, which one should we choose? Keep in mind, these are the costs, right? Because the arrow is pointing down. So if we're comparing the cost, which one should I choose, or should we choose? A new plant or remodel? Yes, you're absolutely correct. we want to minimize the costs. Therefore, we want to minimize the future value of these costs. And the smallest is this, right? The new plant has the smallest future worth because we have 36,000 here versus 82,000 here. So we're gonna choose the new plant. Alright, now let's talk about benefit-cost ratio analysis. And so this is not, while the future worth analysis is equivalent to present worth and annual worth analysis, this benefit-cost ratio analysis is not, on the other hand. And what we really do when we do this analysis is we look at a given minimum attractive rate of return, right? So we assume that we know some minimum attractive rate of return, which basically is a rate that a company sets at which they want to, do at least as good or get at least as good of rate of return as the minimum attractive rate of return. And if it's smaller, then they could just instead use minimum attractive rate of return. And so at a given minimum attractive rate of return, an alternative is acceptable, provided that present worth of benefits minus present worth of cost is more than 0. Alternatively, it means that present worth of benefits is larger than present worth of cost. Or if we could look at it from the equivalent uniform annual worth, and then again, equivalent uniform annual benefit minus equivalent uniform annual cost, right? If we're talking about annualized amounts, should also be more or equal than 0. And these criteria could also be stated as a ratio because we can move things around. For example, we can move the costs to this side, and then they're gonna be with a positive, and then we can move the cost here to this side, and again they're gonna be with a positive. And we can divide both sides by the cost, respective cost. Here is the present worth of cost, and here is the equivalent uniform annual cost. And then it will give us this expression. So basically the ratio of benefits to cost, either in terms of present worth or equivalent uniform annual cost or worth, is more or equal than 1. So again, it's just the idea that we want the benefits to exceed the cost. So now let's take a look of how do we apply it in different situations. So the most complex situation we could have is when neither input nor output is fixed, right? And that's the typical scenario. So in that case, what we do is we do this so-called incremental benefits to cost ratio analysis, and we try to compute incremental benefits to cost ratio, and then decide, right, again, given a certain minimum attractive rate of return, we compute the benefits to cost ratio, either using the present worth or equivalent uniform annual cost, and then decide, right, if in fact the ratio is more or equal than 1, then we choose a higher cost alternative. If this incremental ratio is less than 1, then we're going to choose the lower cost alternative. There's other two situations that are somewhat simpler. One example is when we have a fixed input, and as we discussed, what it means is that we have amount of money or other input resources that are fixed. In that case, what we do is we're maximizing benefits to cost. Or in the fixed output situation, when we have a fixed task or benefit or other output, then again we maximize the benefit to cost. So now let's take a look at the example. So here we have two devices, device A, and these are the cash flows for the device, where we have some initial cost, and then we have this uniform annual benefits. And then device B, where again we have initial cost, but then rather than having these constant uniform benefits, we have this arithmetic gradient series. So you can see that it's clearly arithmetic gradient because between each of the consecutive savings that we have each period, there is exactly 50, right? 50 difference, right? If we subtracted any this one from this, we have 50. This one from this, we have 50, and so on, right? So 50 is our gradient amount, arithmetic gradient amount. So again, what we're gonna do is we're gonna apply benefit to cost ratio analysis. So when you look at this, the question is, what are our benefits? Well, benefits are these savings, right? The arrows pointing up are the benefits, and the arrow pointing down is the cost. So then it's easy to get the benefit to cost ratio. Again, like I mentioned, when we comparing the alternatives, we do an incremental benefits to cost. So simply by subtracting these two cash flows, we're gonna get cash flow, incremental cash flows. So notice when we subtract these two, we are subtracting it from the largest alternative. So see, it's gonna be B minus A, the largest initial cost, right? Device B has the higher initial cost compared to device A. 1350 is higher than 1000. So device B, from those costs and benefits, we're going to subtract device A cost or benefits. So B minus A. So now we're going to subtract from 1350, we're going to subtract 1000, and so we're going to get 350 as this incremental initial cost. And then when we subtract from device B 300, this uniformly for each year, this is just going to be a 0 here, and then it starts with 50, 100, 150, 200, and so again we're just going to get something like this. So in this case we just eliminated the A, we only have a G for this example. So now we can find the benefit to cost ratio. So benefit, incremental benefit divided by incremental cost, we're using present force. First for A minus do nothing, because in this example we also have do nothing. So that's simply, if we do that, that simply would be just benefit of A divided by cost of A. So benefit of A is all these 300 uniform series, right, of 300. There's 5 different, well, different, they're all the same, 300, 300 and 300 and 300, right, five times we have this 300. So to find the present worth of these uniform series, we just multiply this 300, which is the A value. We want to find its P, right? So PA is going to be the discount factor. So PA, 7% is our interest rate in this example, and because there's 5 of them, we're going to have N5. So then divided by 1000, which is our present worth of cost. So then we evaluate this, we get this much divided by 1000, we have 1.23. So question to you is, what do we compare this incremental benefits to cost? What value do we compare it to? This 1.23. You're absolutely right. Yes, we're gonna compare it to 1. So the incremental benefit to cost ratio for alternative 1 is larger, for alternative A minus do nothing is larger than 1, and therefore we're selecting the higher cost alternative, which is A. So compared to do nothing, we would select A, but we still have the B. So then we also want to do the same, this incremental benefit to cost ratio. We need to compute it for the B minus A. And so we do the same for that, and we have 50, which is our G. We want to find the present, so PG. PG is a discount factor, 7% 5. And then 350 is our cost for incremental cost. And they're already in the present, so we don't need to multiply by any discount factor. So then, evaluating this discount factor, multiplying it by 50, we get 382 on top, 350 at the bottom. Dividing those two, we get 1.09. So again, what do we compare this ratio, right? This ratio evaluates to 1.09. We compare it to 1. 1.09 is larger than 1. So because the benefit to cost, is this incremental benefit to cost ratio is larger than 1, we're going to select the higher, once again, the higher cost alternative, which is B. So A1 over do nothing, but B1 over A. So we're going to select B. Another example, we have here benefit to cost ratio analysis, machine X and machine Y, two machines. We have initial cost, uniform annual benefits, and end of useful life salvage value, and we also have useful lives in years. So notice here the useful life in years are different. We have 6 and 12, so they're not the same. So again, we need to make sure, right, we're comparing apples to apples. So one way to do it is to look at the equivalent uniform annual benefit to cost. So first we're going to compare machine X to do nothing. Why? Because machine X has lower initial cost than machine Y. So the increment is going to be Y minus X. But first we also want to compare X to nothing to see whether it's worth going with X versus doing nothing. So then what we do is we just compute here, right, the benefits. So the benefit is 95. So that's what we see. This is annual benefit, already annual. But we also want to find the cost. So there's two values that go into cost. One, the initial cost, and then the salvage value is going to reduce the cost. So we will add the salvage value, and again, it depends on the type of analysis. But in this case, we're using the salvage value to reduce the initial cost. And this is the present value, this is the future value. What we want to do is we want to turn both of these into the annual values. So this 200 is going to be multiplied by A given P, because 200 is the present. We want to make it annualized. So A given P, right? We want A, find A, this is P. AP in the same order we have the in discount factor. And then 10% is our interest rate in this problem, and this is 6 years here because we're just looking at X, simply only at X. And then this 50, right, is a salvage value, but we're using it with a minus because this reduces the cost, right? This is actually the salvage value. It's a benefit, or this it's rather than a benefit, we're looking at it as a reduced cost. So 50 is a future. We want to find A given F. So again, AF, 10% 6. And so when we plug in those A and P values from the discount found from the discount factor tables, then this is going to be 40. So 95 divided by 40 is 2.38. So once again, what is the number we're going to compare this incremental benefit to cost ratio to? Yes, of course, it's still 1. We compare it to 1, and this ratio is more than 1. Therefore, we're going to choose the higher cost alternative, which is X. Right? X is higher cost compared to doing nothing. So then we do similar analysis for Y minus X. And so here what we're looking at is the equivalent uniform annual benefit of Y minus equivalent uniform annual benefit of X. And so that's what gives us the right. This is how we compute the benefits, right? So again, incremental. The benefit of Y minus benefit of X. Benefit of Y is 120, right? So 100 is uniform annual benefit for Y. So 120 minus 95. And then here we analyze the Y, right? This is simplifies, right? As long as we analyze the Y, then we just look at the Y and the X as separately, right? So we already computed the equivalent uniform annual cost of X, and that was 40, right, previously. So we're just going to use the 40. So that's our equivalent uniform annual cost of X, which we computed in the previous previously, right here when we compared the x to do nothing. And then here we're using 12, right? So notice there we used 6, here we're using 12 because we're computing equivalent uniform annual cost of y. All of this in the square brackets is us computing the equivalent uniform cost of y. So what is the cost? Well, first this is a present value, right? Initial cost, present value, and then this end of useful life salvage value is a future. This is gonna be the cost. This is gonna be the reduced cost. Therefore, we're gonna have minus here, and that's what you see. This minus 50. This is a p. This is the f. Therefore, we have a given p, a given f. 10%, 12, right? Because the useful life at 12. So this equals to 96. All of this together. And so 96 minus 40 is 56, and 25 divided by 56 is 0.45. So once again, we're going to compare it to 1 because we want the benefit to exceed the cost. So we compare it to 1, 0.45 is less than 1. So benefit does not exceed cost, this incremental benefit to cost. And so we're choosing the lower cost alternative because it's lower than 1, right? The ratio is lower than 1. So we're using the lower cost. When it's higher than 1, we're using the higher initial cost. So this means that we're gonna choose machine X. Machine X is the final answer. Alright, I hope this is helpful. Let's take a look at another example. Here we have multiple alternatives, A, B, C, D, E, and F. What we're gonna do is again look at how they are in terms of initial cost. We're gonna start with a smaller alternative, so smaller initial cost, and proceed pairwise all the way to the highest initial cost. So you can see that D is the smallest initial cost. D is the smallest, then B, then I believe A, and then C, E, and F. And so we have those present worst of benefits, we have benefit to cost ratio. So D, right, when we're comparing D to nothing, this is 1.34, it's higher than 1, so we're going to choose D. And then we're going to compare D to B, because B is the next one. So again, rearranging the alternatives, rearrange that, just like I said, D comes first, then B, then A, then C, then E being the highest initial cost. Then we calculate the incremental benefit to cost ratio, and if it's more than 1, then we choose the higher cost alternative. So again, D, I already said D compared to the nothing wins, so we can select D because it's 1.34 more than 1, so we could do D. And then we compare B and D, right? These two that are next to each other when we put them in order of increasing initial cost. So these two are gonna be compared. So B minus D, the higher cost is B, the lower is D, so B minus D, higher minus lower. So we look at this incremental, that gives us the incremental benefit to cost ratio of 3.36. So then again, this is more than 1, this 3.36 is more than 1, so we're going to select the higher cost, because it's higher than 1, we select the higher initial cost, B. And then the next one is A, so we're comparing A minus B. Again, computing this, get 1.3 as incremental benefit to cost ratio. It's again higher than 1, so we select the higher initial cost alternative. And so A is going to be the current champion, and we compare it to the next in terms of increasing cost, which is C. So C minus A is going to be 0.7 incremental benefit to cost ratio, which is lower than 1. So we select the lower cost alternative, which is A. So we keep the A as a champion and look at the next one, which is E. E minus A is going to be 0.33. So again, lower than 1. So selecting the lower cost alternative. So A is the final selection. A is a champion. So we're gonna go with project A. Alright, so now let's take a look at the graphical representation. We have present worth of benefits versus present worth of cost, and this is when they're equal, right? So where we want to have them, we want the present worth of benefits to exceed the present worth of cost. So we want to see projects fall into this, right? This is where we want to be in this part of the quadrant, right? We want to be above the blue line of when the present worth of benefits equal to cost. So that's when the ratio benefit to cost is 1. So this red line is benefit to cost equals to 0.5, which is less than 1. So we don't want to be there. And this green line that just appeared here is when benefit to cost is 1.5. So we would want to be somewhere here, right? Because it's more than 1. Again, this is even higher. This is benefit to cost is 2. So again, if you look at these, right, and then plot some of our projects, right, this is where they fall. However, right, we gotta be careful, right? So you see here where A, right, it gives us even higher benefit. And so if you look at this, right, these are above the line. And then what we're trying to do is, again, look at comparing, right? If you were to compare, say, D to 0, right, this falls above the line. When we're comparing B and D, we again look at this starting from the D point, right? We draw the line that would be at 45-degree angle, so it exceeds it. So we would choose the B. Then starting at B, we would again draw the line at 45-degree angle. So this angle is higher, right? So we choose A. But then again, starting with A, we draw the 45, and you see that C is under the 45-degree angle line, right? So if you were to take this light blue line right here and then translate it in parallel, right, and draw a parallel line to this line at A, it would go like this, which these C and E are both under. And so that helps understand graphically of why we didn't select C, E, and also F either. F would be right there, which also does not apply. So now, right, as I said, what we did before is we used the salvage value as a benefit. We looked at it from the standpoint of reducing the cost. So of course what that means is that there could be some variations on the benefit-cost ratio, right? Because you could say, well, couldn't we just take the salvage value and use it as a benefit? And here are some examples of variations of benefit-to-cost ratios. And this is why benefit-to-cost ratio is not as clear-cut as some of the other methods that we discussed. And here, as an example of government benefit-to-cost ratio in public sector, what we do is we take, as a benefit, we take all consequences to the users or the public. And as a cost, we take all the consequences to the sponsor or government. And then evaluate it like that. And we can also use a present worth index, and that's what usually is used in private sector, and that's a benefit to cost ratio where we take all the consequences except the first cost and we divide it by the project's first cost. So in this case, right, we don't use the salvage value, we only use this project first cost. And even if we had some kind of payments or maintenance cost, they still go as benefits but with a negative sign. So again, as you see, there are variations on this benefit-cost ratio, but for all benefit-of-cost ratios, we use the same criterion that benefit divided by cost should be more than 1, which means benefit should exceed the cost. And again, various benefit to cost ratios may differ in value, but they should provide consistent recommendations. So here's an example of government benefit to cost ratio analysis. We have right turn lanes versus left turn lanes. And so here, in terms of initial cost, this is incremental value between the having just right turn lanes or also adding the left turn lanes to the right turn lanes. The incremental is going to be 3 million here. And in terms of annual maintenance, this is the incremental cost. And we can also find the uniform annual benefits difference. And notice the useful life is the same. We have this benefit. So using the government is basically what the benefit is benefit to the public, and the cost is the cost to the government. So what is the benefit? This is a benefit to the public, which is 1.6, but there is also some disbenefit from maybe doing the construction. So this disbenefit is also included, but with a negative sign. So you can see this negative. And that this benefit is only happened in the present, right, while during the construction. But this benefit is a uniform annual benefit. And so this needs to be turned in the present. So this 1.6 is annual. We want to find its present equivalent. So PA, the discount factor is also PA, 10% 15, because we have 15 years and 10% is interest in this example. And then 900 is this benefit. It only happens at time 0, right, during the construction. So this is this benefit to the public. For example, right, if we are constructing the right turn lanes during the construction, there, the people would be there would be increased traffic, or they have to go around. So that's the estimate for this benefit. And then the rest is the cost, right? Initial cost, the government incurs initial cost. The annual maintenance is also initial cost is also the cost for the government, even though it's not initial, it's annual cost, right? So this initial cost is already in the present, so this we don't need to multiply by anything. So you see 8.9 million, but the annual maintenance is a cost by the government that is annual. So this A we need to find its present worth equivalent. So PA, so multiply by P given A, 10% 15. So when we evaluate this, we get 10.04 million, and when we evaluated this top, we get this much. So when we divide these two, we get 1.122. So this is higher than 1, therefore it's better to construct the right lanes rather than doing nothing. So we would select the doing the right lanes. However, the left turn lanes have even more, they're even more expensive. See, it's in addition to 8.9 million, there is this incremental cost for the left turn lanes of 3 million. So the left turn lanes actually cost 11.9 million. And so what happens is that we want to see, okay, so we should construct the right turn lanes, but should we also construct the left turn lanes? And therefore we're going to also look at the benefit to cost ratio, the government variant of it, between the left and right turn lanes. And that's what we have, left minus right, again in terms of present force. And so this is just incremental analysis, right? In terms of incremental analysis, we have initial cost. There is also difference in terms of benefits. So this annual benefit and this benefit are the cost to the public, right? Or the benefit to the public. So here we have 2.2, because this is a higher cost alternative. 2.2 minus 1.6, that's 0.6. So that's the difference. So this is where the 0.6 come from. That happens annually. So we find the present worth equivalent of it. So it's gonna be PA, and so discount factor is PA to make this annual amount at its present worth equivalent. 10% 15. And then here, right, this benefit, if when we subtract from 2.1, right, because the left turn lanes are higher initial cost, we subtract from left, we subtract right. 2.1 million minus 0.9 million, right, because this is 0.9 million. So it's 1.2 million when we subtract these two. And this is what you see, right? And this is a disbenefit, so it's going to be with a minus sign. So this is how we evaluate this benefit. And then for the cost, we're using the initial cost and the annual maintenance. And initial costs are already present. So this is incremental amount. This is 3 million for initial cost. So we have 3 million. And then the annual maintenance are going to increase by 75,000 compared to right turn lanes. So it's going to be 75,000 as a A. We're going to find its P equivalent. So PA, 10%, 15, that's our discount factor. When we evaluate the top and the bottom, we get this, and the ratio is 0.9, right, a little over 0.9, but it's less, right, it's lower than 1, and so if it's lower than 1, then we should go with the lower initial cost alternative, which means the right. So the final answer is to do the right turn lanes only. Do not add the left turn lanes for this project at this interest rate. Alright, another example of present worth index analysis, and as you remember, present worth index analysis, it's used in the private sector. And it's basically everything is put in as a benefit except for the initial cost. As the initial cost is what goes at the top, at the bottom, at the bottom. So again, minimal, total, and incremental, these are so minimal in total, right? If you have minimal construction versus total construction. So very similar to the previous example, but we are using this as the present worth index analysis, so for private sector analysis. So again, right, everything goes on top, and only the present worth of the costs, this is where we get. So minimal versus do nothing. So we have initial cost here, and then this benefit is also happening at the beginning, so it's also initial cost. So we're adding 8.9 and 0.9 million, and then the benefit is the rest of it, right? The benefit is 1.6 annual and annual maintenance, so this is both annual, so we subtract from the benefit, we subtract the maintenance, right, because this is a disbenefit. And then this difference is they're both annual, so this is the annual amount. We want to find this P equivalent, present worth equivalent. So PA, and so here we have discount factor PA, 10%, 15. Evaluating the top and the bottom, we get a ratio of the value of ratio 1.125, which is higher than 1. So we choose the higher cost alternative. So we choose minimal. And so again, right, what we're gonna do is we also compare minimal to total, right? Total is the higher cost, so total minus minimal, we're putting, right, again, this initial cost and this benefit, they all happen in the present, so they are the initial cost. These are the initial cost. So this 3 million, we're looking at incremental, alright, so 3 million here, and then the difference between these two, right, 2.1 minus 0.9 million is 1.2 million. So this is 1.2 million comes from subtracting from total minimal for this benefit. So this is 1.2 million. So that goes at the bottom as a cost. And then the rest, everything else is going to be the benefit, except the maintenance is going to be this benefit. So it's going to be with a negative sign. So here's the annual benefit. It's going to be the difference between these two. So 2.2 minus 1.6 is going to be 0.6 million. So you see 0.6 here. And then minus, right, this incremental difference in maintenance. So it's minus 75,000. And these are, again, A, right? This is annual. And we want to find the P equivalent of this A. So P, A, in the same order, PA as a discount factor, 10%, 15. evaluating this, all of this, we're gonna get 0.951, and notice, right, the values are actually different, but it's very consistent, right, in terms of the ratio values are different. These values are the same as the previous example, and the 0.9 is lower, right, so we're gonna go with a lower cost alternative, which is minimal. So the names are just different, but we go in with a minimal, and these were our right lines, right? The numbers are the same in terms of here, but the ratio values are different. See, this was 1.125, and in the previous slide, it was 1.122, and the second one was 0.942, and on this is a 0.951. But they're still consistent. The result of analysis is consistent even though we're using a different method, right? This is a private sector method. Alright, now let's talk about the payback period. So payback period is a period of time that's required for the project's profit or other benefit to equal the project's cost. And it's an approximate economic analysis method. And the effect of the timing is ignored in this method, and that's very important to realize, right? And so be careful in terms of using this method because like I said right now, it's approximate and the effect of timing is ignored, and all economic consequences after payback are also ignored and may not be consistent with equivalent worth and rate of return method. So this payback period method is not always consistent with equivalent worth methods or the rate of return method. So now let's take a look at the example that applies this method. So we have different years, we have different alternatives A and B. We have these five different years. We have some initial cost, and then we're gonna start recouping those. So these are the benefits that we see in each of the year for A, and in this row we have the initial cost and the benefits for B. And so now when we compare these, right, we can look at the cumulative benefits. So for A, we start first with 200, then 400, accumulate these two, and then add this one. This is gonna be 1600, so you can see this is in year 3. So 1600, and this is where it crosses, right? It crosses this 1000. So here it was still under 1000. Here it's crossed the 1000. So it takes 3 years to pay back the A. Right. So red line is the 1000 that we want to pay back this initial cost. Again, we're just accumulating it without ignoring the effect of time. We're not using any compounding, nothing, right? No interest rate. We're just adding these values. So this is an approximate technique, right? So this is 200, 200, 400, right? This is cumulative 200 by year 2. And then adding another 1200 to the 400 is going to get us to 1600. So this is where we cross this 1000. So similar thing, right? So this payback is approximately 2.5 years. Similarly for alternative B, what we're gonna do is we're gonna start adding. So these two together is gonna be 24, right? By year 2, we're gonna get to 2400, and then we're gonna get to 3600. So again, where do we cross the line? We'll cross it somewhere here. So payback period is 2.33 years. So it seems like, right, using this analysis, we get the alternative B has a smaller payback period than alternative A. So here's another example of application of payback period. Here we're selecting between two alternatives in these two rows. One alternative is Atlas and another one is Thumb. And here's our cost, uniform annual benefits, and salary values. So once again, we can compute accumulative benefit in years for Atlas, right? So we're increasing this by 450, 900, and so on. So you're reaching the 2000 cost somewhere here, right? And that gives us a payback period of 4.4 years. And then for Thumb, we also construct this cumulative benefit by adding 600. So this is 600, this is 1200, this is 1800, and so on, right, until we cross this 3000 line, which is right here. So we crossed it at year 5, and so this thumb sum has a longer payback period, so we would choose the atlas if we wanted to have a shorter payback period. So once again, have two alternatives, tempo and dura. Here's the cost, annual benefits, useful life, a cumulative benefit for tempo. It crosses at 3000 in year 4, but look, we're ignoring, right, what happens after, right? In years 5 and 6, right, it's still just gonna be, this is our cumulative benefit. And then for dura, right, we crossing it, right, the payback period is at 5, but it continued to accumulate benefits. And so this illustrates, right, that even though dura has a longer payback period, but you can see, right, that we continue to accumulate higher benefits. So again, there's a big question, right, of being careful in terms of using payback period, because often the payback period is used. However, it's important to remember that it's approximate technique, that we are not using the time value of money in this, and we're ignoring what happens after the payback is achieved. Now let's finally talk about sensitivity of break-even analysis. And what sensitivity analysis is basically we are trying to do some projections of expenditures and returns, and trying to understand how they affect economic decisions. So to what extent do variations in the data affect the decision, right? Maybe like we were talking about estimation of cost and benefits in chapter 2, it's hard sometimes to estimate the costs and especially the benefits precisely. So sometimes, it's useful to look in terms of, all right, so this is our estimate, but we know that usually the costs are underestimated and the benefits are overestimated. So if we look at this possibility of evaluating these costs and benefits incorrectly, and if we add this adjustment, how does this affect our decision? Will the decision be different? So that's sensitivity analysis. And in terms of break-even analysis, it's a form of sensitivity analysis. And in this analysis, the main questions are, in what conditions two alternatives are viewed as the same, basically the same. And one application is a stage construction, right? When we could build everything at once, or we could build part of the facility first and then build additional facilities later. So this stage construction is useful to understand, okay, if we do the stage construction, how, under what conditions it's the same as if we build it all at once, or the other way around. So here's a quick example of break-even analysis. We have construction costs. We can build a full capacity facility, or we can have a two-stage construction. So full capacity construction cost is $140,000, and in two-stage we pay $100,000 now, which is less than full stage. But then we again in n years from now we're gonna build additional facilities, which will cost us $120,000. So we have flexibility in terms of how many years from now we're gonna have that additional construction built. So we want to know what's the year end that gives us the break-even value, basically, of year end between the full capacity and two-stage. So the present worth of full construction is 1,400,000. Not 1,400,000, sorry, 140,000. And then the present worth of cost for two-stage is going to be the 1,000, which is already present, and then we have this additional future amount n years from now. So this is future, we want to find its present force equivalent, so P, this is F, so we multiply it by discount, also in the same order, PF, 8% N. So then we can solve this equation, right? Equate these two together, the present force of full with the present force of two-stage, equate this together, and find for which N we would break even. And again, another way to do it would be to do it graphically, right? So this is graph for two-stage, depending on different years. This is for 0 years, right? If you right away build the two-stage, you see this is a 100 plus 100,000 plus 120,000, so that would be 220. Right? Of course, you know, we're not gonna do the two-stage construction in the year 0 if the full capacity is much cheaper, right? The full capacity will come somewhere here at 140,000. So this is two-stage, and it's gonna reduce depending on where our year in, and so it will cross this full capacity of cost of full capacity, which is 140,000. This red line. And it will cross right here, right? This is our break-even point. So break-even was approximately 15 years. So here's an example of another break-even analysis when we have 3 alternatives and we have an initial cost of B, or there's a flexibility in terms of initial cost of B. We have A, initial cost and uniform benefits. B, initial cost is unknown, uniform benefits. And here is a C, and so we can find the net present force of A simply, right? This is a negative initial cost, right? Negative to 100, it's already in the present, and this is the annual, so we want to find the P equivalent of it. So P, this for 110 is A, PA, the same discount factor in the same order, PA. This is P, this is A, in the same order, PA. 6% is our interest rate here, and then 20 is the number of years here. So this relates to this much. Then the same thing for P, net present force of the C. The only difference is the actual values here. So this relates to this much. And then we have this net present force for B, so we can find the equivalent of 639 annual, equivalent in the present, so that was 7,329. So then we can compare these. So 7,329 minus X, we can compare it to net present force of A, which is 2,703, and net present force of C, which is 3,029. And so for alternative B to be selected, the net present force of B should be more than the net present force of C, right? Because the net present force of A and C, when we compare these, the C has higher net present force, so the C beats A. So then we're looking at the net present force, maximizing it. If you want to select B, the B should exceed the net present force of C. So then the 7,329 minus X should be more than 329. And so solving it, we get that X should be less than $4,300. So the initial cost, as long as B has initial cost at less than $4,300, then we will go with alternative B. And graphically, it can be represented like this, right? Where this line here, the light blue line right here, that's slanted, is this equation 7,329 minus X, the net present force of B, right? And then this 27, right here, line, this is 2,703, that net present force of A, and this one right here is a 3,029, that's net present force of C. And so you can see here we're right for what X, right, this right here, this is the 4,300. So everywhere here we're happier with the B, over here we're happier with the C, and that's a break-even point. So again, we can do similar thing for break-even analysis for right turn lanes versus left turn lanes, thinking in terms of the number of years, right? So if we have, in the previous case, I believe we had 15 as the number of years, but what if the number of years is different in analysis? How would that change our decision? And what's the number of years that we could use or continue to use the left turn lanes, right, in order for us to break even with having just the right turn lanes. So again, using the n here instead of 15, but it's very similar to the examples we considered, and then we can plot this graphically. We can discover, right, that the number of years, right, this is a break even for right turn lanes, this is break even for left turn lanes, and this is for break even for incremental investment. So it should be somewhere, you know, more than 16 years for us to consider, you know, adding the break left turn lanes to compare it to the right turn lanes. And last but not least, I want to take a look at this example 9.15. So I'm gonna go ahead and open the Excel file and take a look at that. So here I open the Excel file where I already have entered the initial cost, units per year, net unit revenue, life in years interest rate for our initial estimate, and also in terms of the adjustment. So like I said, in terms of the cost tend to we usually tend to underestimate the cost. So what we're gonna do is we're gonna say, well, it's very likely that we underestimated the cost, and the typical percentage of that the costs are being underestimated by is 10%. So we're gonna give this adjustment, right, assuming that our initial estimate might not be correct. We're gonna have this adjustment of 10%. And also in terms of benefits, right, so the units per year and net unit revenue are our benefits. So we tend to overestimate the benefits. So we're gonna also try to compensate for this typical overestimation. You will say, well, we're really excited about these units per year, but maybe we're not gonna get as much demand for our units. So typically the benefits are overestimated between 15 and 20%. So we would assume that we are overestimating this demand for our units by 20%. So we're going to have this negative 20% to compensate for our optimism, right? And then to correct for the net unit revenue, because maybe they're not going to be selling for as much as we expect them to sell. So again, we're gonna do this adjustment of this benefit by 15%. And also we will think, well, maybe we think that the project will last 8 years, but you know, maybe we're too optimistic about it. Maybe it will only last 3 years. So let's go ahead and see how that would change our decision. But first, what we're gonna do is we're gonna let's go ahead and get the adjusted values, right? So the adjusted values, what's gonna happen is we're gonna get the adjusted value here. It's simply gonna be this multiplied by, right? So I clicked on this to select. This is my B2 cell, and then I'm gonna multiply this by 1 minus the percentage, right? So 1 or not minus, plus the adjustment, right? So we're gonna get this. So this is gonna be my adjusted value, and I'm gonna go ahead and format this, and I'm gonna also format similarly this value here. So then what's gonna be my units per year? Again, I'm gonna follow the similar formula. So I'm gonna multiply my initial estimate, and I'm gonna correct it by multiplying this estimate, right? I selected this estimate. Now I'm multiplying it by the correction is going to be 1 plus the adjustment. So then it's going to be, right, so here we have a higher initial cost. From the 70, it's going to now, initial cost will increase to 77. In terms of the units, the benefits are going to be decreased. The number of units, instead of selling 1200 units, we can only sell 960. And then similarly for net unit revenue, we're going to have, right, I'm going to select this cell and then press multiply, and here in the brackets 1 plus the adjustment, and this reduces my net unit revenue from 25 to $21. And then last but not least, we're going to reduce the life. So I'm going to select this, and then I'm going to add this adjustment here, and so that changes my life to 5 years. But the interest rate is going to remain the same, right? So I'm going to just leave the interest rate the same. So now let's first take a look at the initial estimate, right? So if I were not looking at this adjustment and just look at the initial estimate, what would be my revenue per year? Well, revenue per year is going to be number of units per year multiplied by net unit revenue. So I'm going to say equals, then select this cell that gives me the value of units per year, and then type multiply, and then multiply by net unit revenue, which is this one. So I'm selecting this one, and that's how much I have the revenue per year. And so what is going to be my present worth of benefits, right? So to find that, I'm going to use the PV function. PV, right, returns the present value of investment, right? So now what I'm going to do is I'm going to say open this, right, open the bracket, and then the next thing is the rate. I'm going to select the rate as my first parameter, which is 12%. Then I'm going to choose the number of periods, which is 8, because we have 8 years. Then I'm going to choose a payment, right? Payment is the annual amount, right? So what is my benefit in terms of present worth? This is my revenue per year, right? This 30,000. Keep in mind, right, that for PV, this payment was given with a minus sign. So I'm going to have minus and then select this. And then this gives me this much as terms of benefit. And now I want to find the cost. So present worth of cost. I have this initial cost here. They're already in the present. So I'm just going to say equals this, right? And then finally I have benefit to cost ratio. How I do that? I'm going to just say equals. Here's my benefit. I select it. Then divide by the present worth of cost. I select this. And that gives me this much. So you can see this is actually 1 point approximately 3, 113, right? So then it's more than 1, right? So if it's more than 1, I would select the higher cost alternative. However, if I have this adjusted values, how would that affect my calculations? I'm just going to go ahead, select this, and copy it, right? So I'm going to copy this here, right? I'm going to select this cell and then say paste, right? So I'm going to paste this. And what it does, it just pastes the formulas, right? So this one is just units per year multiplied by net unit revenue. So that gives me this, right? And so on. This is just PV, right? In terms of this is my rate. So here, right, as blue, this is my rate. As green, this is D5. This is my life in years. So number of periods. And this is my revenue per year. So that gives me the benefits, right? And then the costs are just this cost here. So now when I divide benefit to cost, my ratio is less than 1. So this leads me to a different decision than this, right? So what this means is that what if, right? If we did this what if analysis and look at what happens if we adjust the values, we would come to a different conclusion after adjusting the values, right? So that tells us that it's sensitive to the estimate errors. Alright, so this is an example, of how we can do the analysis. Please take a look at it again and read chapter 9 in the book, and I hope this has been helpful for you. Thank you, and I talk to you soon.